Hi guys, today we are going to talk about lesson number 9, and this is section 1.8, combination and composition of functions. The basics of these topics is something that you should remember very well from last year. So we're going to go through the easy ones relatively quickly, and then we'll save some extra time for the word problems, the more complicated algebra, and the more complicated examples of the domain. So just as a quick reminder about what function notation is, because you absolutely have to make sure that you're doing that right in order for any of this to work. So function notation, of course, means that I give you a function. I give you a value of x for which to evaluate it. Everywhere there's an x, you're going to put a -2. You're going to use parentheses when they're applicable. You're going to calculate, and then your final answer, you should write it as f of something equals the number. Again, you've done tons like this, so that should be very, very simple. Slightly more complicated is when you have a function and you're being asked to plug more than just a number in this case, x plus 2. You have to remember that when you're doing function notation, everywhere there's an x, you have to plug in x plus 2. In this part right here, you are distributing. In this part here, you are foiling. And after you foil, you have to make sure that you distribute the minus. Again, these tiny little algebraic mistakes, they happen, of course, from time to time, but anything you can do to avoid them just makes everybody's lives a little bit easier. And then your final answer by combining like terms, 4 minus x squared. We would probably write that as -x squared plus 4, standard form, but you get the idea. Turns out that combination of functions is something very straightforward. Basically, you can take any two functions or more and combine them to create new functions. How do you do that? Well, you use the 4 basic operations: sum, difference, product, and quotient. Take a look at the 2 different kinds of notation. This is what your book uses. They would say f plus g of x. What that actually means is f of x plus g of x. And then notice that that carries all the way through for each of these 4. I do not care which of the notation you use. In fact, I probably will use the right side notation more because I like it better. But please just be aware that your book does use the left-sided notation. So feel free to convert it or at least make sure you understand what the questions are asking. I could ask you for the domain of any of these, but more than likely, I'm going to ask you for it only for the quotient. Of course, when you're doing the domain, you cannot have a denominator equal to 0. So that is something that you always have to watch out for. Let's kind of start off just basic, easy. Here are 2 functions, f and g, and I'm going to ask you to perform the 4 combinations. So the first one is f plus g of x. Again, if you would like, you can rewrite that as f of x plus g of x. Insert the entire f, insert the entire g. All you're doing is adding, so combine like terms and give your final answer in standard form. In the next one, you're doing subtraction. So all you have to do here is make sure that you are, in fact, distributing the minus. When you distribute the minus, make sure that you then combine like terms and you get a final answer here. Addition and subtraction should certainly be no problem for anyone. Multiplication, it can get harder as the functions themselves get more complicated. In this case, it's a basic FOIL. So first outers, inners last, and then be sure to give your final answer in standard form. Finally, the quotient. So if you're putting f over g, and just to be clear, f over g is not the same as g over f. So order does matter. You have to follow exactly what the question is asking. And so here, 2x minus 3 over x squared minus 1. Now, you can, of course, factor the bottom as x plus 1, x minus 1. The reason why I didn't is because it doesn't reduce with the top. So if it doesn't reduce with the top, whether it's factored or not really doesn't matter. So I would take either answer. And then as I mentioned earlier, you are going to be asked to find the domain of most quotient problems. So if I did put the f over the g, what would be the domain? Well, here I would like to factor the bottom, which I've already done. And that will tell me that x cannot equal plus or minus 1. So how do you write everything except for -1 and 1, not including? You do negative infinity to -1, -1 to 1, and then 1 to infinity. And there should be parentheses on everything because you're never going to get to infinity. And because it's a denominator, you're going to use a parentheses for the ones. Composition. So composition, again, something that you should have seen last year, but in case you forget, it basically means you're putting one function into another function. And more important than ever is the order. You always have to work from the inside out. Sorry, new stylus here. So you always have to work from the inside out. So again, starting off with a little bit of notation. So over on the left-hand side, this is the notation that your book uses. You could see it on the AP test next year. F circle G of X looks like fog. That little open circle means composition. Another way to write it is like this, with the G of X on the inside and then the F on the outside. The way that you would say this in words is F of G of X. If we're talking about order mattering and working from the inside out, that means you would first use the G and then apply the F. Over here on the left side again, G circle F looks like golf. That rewrites to this, G of F of X. Again, I do not care which of these notations you use. Most of you will probably prefer the right, as do I, but because your book uses the left, you do have to make sure that when you see the open circle, you know that that means composition. So here's a new function, F and G. I have to give those to you if I want you to do stuff with them. So in the first one here, I want you to do G minus F of X. And again, order matters. So G minus F of X means that you're doing the G function, 2x minus 1, minus the F function, x squared plus 1. Whenever you are doing subtraction, you need to make sure that you are using parentheses. So I'm going to get a negative x squared. Then I have my positive 2x. If I distribute this, I get a negative 3 and a negative 1, which combines to be a negative 4. So that is the resulting function that I get if I do the G function minus the F function. Please don't change my problems. Don't set it equal to 0. Don't divide by anything. You cannot change my problem. That is all I'm looking for. Now take a look at F of G of negative 4. So when you see those double parentheses, that means composition. Composition means work from the inside out. So G of negative 4, this is just function notation. Go to the G function. Everywhere there's an X, you're going to put a negative 4. So 2 times negative 4 is negative 8, minus 1 is negative 9, which means you're going to replace G of negative 4 with whatever it's equal to, in this case, negative 9. F of negative 9 means go to the F function. Everywhere there's an X, you're going to put a negative 9. And of course, you're going to use parentheses there when you square it. If you square a negative 9, you get an 81 plus 3 gives you a final answer of 84. Generally speaking, if you're putting numbers in, you get numbers out. If you're putting variables in, then you get variables out. In the next slide, same two functions, but I'm asking you now for two different compositions, G of F and then F of G. So here, G circle F, that's equivalent to G of F of X. So you're going to start by replacing the F of X with whatever it's equal to, x squared plus 3. Then you're going to go to the G function. Everywhere there's an X, you're going to put that whole thing, x squared plus 3. Don't forget the 1. Distribute the 2, x squared plus 6 minus 1 is going to give you a final answer of 2x squared plus 5. F circle G, that means that you are finding F of G of X, which again means if you're working from the inside out, you're going to start by replacing the G. So now go to the F function. Everywhere there is a X, you're going to put a 2x minus 1, the whole thing squared plus 3. 2x minus 1 squared, that is, of course, a FOIL. So first, outers and inners, last, plus 3. And then your final answer, 4x squared minus 4x plus 4. I say again, once you get to that final answer, that's it. You're done. Don't divide by 4. It's not equal to anything. You could factor the 4 out, but why make your life harder? Don't set it equal to anything. That is as far as you can go. Something important to keep in mind when you are doing a composition. When you're doing a composition, you have to consider the domain. Not just the domain of the final answer, but the domain of each individual piece of the problem as you went through. So here I give you an F and I give you a G, and I'm asking you to find F of G of X. So if I'm asking you to find F of G of X, you're again going to start on the inside and replace the G of X, which is the square root of 9 minus x squared. If you then plug that into the f function, you're going to get the square root of 9 minus x squared, the whole thing squared, minus 9. Of course, if you square a square root, it just cancels, giving you 9 minus x squared minus 9. The 9's cancel, which means your new function, f of g of x, is equal to negative x squared. So when I say find the composite function, there it is, negative x squared. Here's the thing though. If I was to ask you what is the domain of negative x squared, you would certainly tell me all real numbers. But when it comes to a composite function, you have to go back and consider the original problems. You have to consider the domain of each of the functions along the way. If the domain of the functions along the way is restricted, then your final answer has to be restricted. So what I mean by that is go back to the f function. You go back to the f function, there are no restrictions, it's all real numbers. If you go to the g function, you do have restrictions. You can't put anything you want in there. You can put in 3. You can put in negative 3, but then you can only put in the values between them, because if you put in anything bigger or smaller, you're going to get the square root of a negative, which is not possible. So because of the fact that the domain of g is negative 3 to 3, that means that the domain of your final composite also has to be negative 3 to 3. So I'll say that again. When you're doing a composition and they ask you for the domain, you have to consider not just the final answer, but you have to consider both of the original functions that you were given. And if those have any restrictions, then your final answer also has to have a restriction. So again, these are the special cases. There are a couple of these in the homework. I would suggest you start by writing the domain of each of the original f and g's, and then you only have to go back and look once you have your final composition answer. Okay, so the opposite of composition is decomposition, which means I give you the final answer and you're trying to tell me which two functions got put together to give that answer. Now, a special note here, you can never make either of the functions just x. That's too easy and way too lame. So you do have to make sure that you have different, unique f, g, h, whatever it is I ask for. So not only do you have to identify the appropriate functions, you also have to put them in the appropriate order. So here is my function in question, h of x equals 3x minus 5 cubed. I am telling you that that was built of two functions, f and g, and I want you to tell me the order so that the g went into the f and resulted in this problem right here. So ultimately, that means I'm looking for an f and I'm looking for a g. And because of the order, the g had to come first. So 3x minus 5 cubed, whichever of the functions appears to be the first thing that happens, the most inside piece of the function, that is going to be your most inside piece of the function, which in this case would be g. So it looks like to me that I started inside with the 3x minus 5. Then to figure out what the second function is, what happened to the 3x minus 5? Well, if you take a look, it appears as though it was cubed. Well, how do you say cube function? You're going to go ahead and say x cubed. So that is the correct answer. And just be aware that sometimes there's more than one correct answer. And obviously, I would take any that are correct, but I would try to always find the easiest one. So again, the reason why this works is if I take 3x minus 5 and I plug it into x cubed, I get 3x minus 5 cubed. You don't actually have to cube it out or anything. You're just trying to tell me what g went into what f that gave me that answer of 3x minus 5 cubed. Let's try another one, the cube root of 8 minus x divided by 5. And again, I'm telling you that you want an f and a g, and the g had to come first. So a couple different answers here. We're just going to do one of them. So if I look for the most inside function, I see an 8 minus x. So I'm going to make 8 minus x be my inside function. And then I need to decide, well, what happened to it? So if I go back and look what happened to it, two things actually happened. The cube root was taken, and there was a divided by 5. So this 8 minus x has to actually go into a variable. So that's the cube root of x. How do you say divided by 5? Well, you simply do divided by 5. Just to be clear, this is not the only correct answer. It just happens to be one of them. Why is it the answer? Well, if you take 8 minus x and you plug it in for this x, you're getting exactly what you're looking for. One more with only two functions, 4 times x minus 2 squared. So again, you want f and g. G is the innermost function, which to me says x minus 2. What is it that's being done to the x minus 2? Well, you're squaring it, and you are also multiplying it by 4. So 4, how do you square something? Well, you simply write x squared. And these are very easy to check. Try putting the g into the f. If you get the h, boom, you got it. Obviously, here in Pre-Calc Honors, we like to do things a little bit, more challenging. So here I'm going to ask you to do it for a threefer. I want to know what's a G that went into an F that went into a K that gave me that final answer. So similar problem here. You're just going to have 3 functions instead of 2. So use the same strategy though. Whatever the innermost function is, which in this case is G, that should be where your problem starts. So if I look as inside as I can, I see an x plus 1, so I'm going to make my g x plus 1. Then what is it that's being done to that x plus 1? Well, it appears as though it's being cubed. So if it's being cubed, then I'm going to need an x cubed. If I put my g into my f, I get x plus 1 cubed. Well, then what has to happen after that? It has to wind up on the bottom of the fraction, and then I have to add 4. So how do I say put it on the bottom of the fraction? I have to have a variable there. Again, very easy to check. Is this right? If I put the x plus 1 into here, I get x plus 1 cubed. If I then take that whole quantity and put it into here, I get exactly what I'm looking for. I wish there was a button I could push that would make it easy for you to be able to do these. The truth is, practice makes perfect, so you kind of just have to plow through them. I think I have one more here. So same idea, K, F, and G. Remember, the order matters, but I have to tell you what the order is. So pause and try it. Maybe we'll pause it and see if people are able to kind of come up with what they think the answer should be. So we'll do that. But again, now that you're back for the answer, the innermost function here is x plus 3. What is being done to the x plus 3? Well, it looks like you're raising it to the 10th power. And then in your final answer, you want one of those on the top, one of those on the bottom, and you don't want to forget to plus 1. Okay, last couple of problems here. So you can also do function operations and composition from a graph. So notice here that I give you the f function and the g function, and then I ask you for a bunch of different things. So you're going to use the appropriate function, look at the graph, take the given x value, and then tell me what the corresponding y values are. So when I say f of 1, that means you're going to go to the f function, you're going to go to x equals 1, you're going to tell me what the corresponding y value is, 0. G of negative 2, go to x equals negative 2, corresponding y value, 0. G of 3 plus f of 3 means go to 3 on the g, take the y value, go to 3 on the f, take the y value, add them up, 4. 5 times f of negative 1, well, whatever f of negative 1 is, which looks like if you go here, the y value is negative 3. You're going to multiply them to give you a final answer of negative 15. So all you're doing is reading the graph. You can do them for composition as well. So g of f of negative 2, work from the inside out like always. F of negative 2 means go to x equals negative 2, find the corresponding y value, which looks like negative 1. This problem now becomes g of negative 1. Now go to the g function, go to x equals negative 1. What's the corresponding y value? 3. I think you get the idea, so let's just skip to 8. You can do g of 1, which means composing a function with itself. Yeah, why not? So starting with g of 1 is negative 1, so this becomes g of negative 1, and then g of negative 1 has a corresponding y value of 3. So if ever they give you the graphs and they ask you to do combination or composition, that means I'm giving you the x's, you're going to find the y's, and work from the inside out where appropriate. Using these two graphs, not only can you combine functions algebraically, which is what this entire lesson has been about, but you can also do it algebraically. Please note, though, that if you're going to combine them geometrically, which means graphically, they have to have a shared domain. So if you go back and you take a look at these two functions here, both of them are only defined from -3 to 3. So because both of these functions are defined from -3 to 3, that means that I can add them together for all of those values. If the f function, for example, was only defined half of those values, I'm only allowed to add them up where they both exist. If only one exists, I have to leave that out. So how do you take these two original graphs and literally add them together to make a new function? Well, you go to the same x value on the f and the g, find each y value, and literally just add them together. So notice that -3 is the first value. So I'm going to go to x equals -3 on each graph. On the f function, it's a 1. On the g function, it's a -2. 1 plus -2 is -1, which means when I add them together, I'm going to get the point -3, -1. Then go to -2. At f of x, when x equals -2, g of x, when x equals -2, add those y values together. -1 plus 0 gives me another -1. -1, -1. I'm going to get -3 and 3. Turns out that's going to be 0. Go to 0, -2 plus 2. That's another 0. Go to x equals 1, add the y values. 0 plus -1 is -1. Go to x equals 2, add the y values. 2 plus -3 is -1. Finally, go to 3, add the y values. 3 plus 1 is 4. And in your final answer, go ahead and connect the dots. So if I connect those pieces, I'm going to get a graph that looks like this. Notice again, the graph only exists from -3 to 3 because that's where the f and the g were both defined. You're only allowed to add them up. So the graph looks very weird. There is no way to predict what the graph is going to look like, and that's totally fine. I'm just going to do this one addition example, but if it was a subtraction, find the y values and subtract them. Multiplication, find the y values and multiply them, and you get the idea. Last problem coming up here is a word problem application. So I'm going to work through it with you. Again, if you don't write anything else down today, you might want to go ahead and write that down. It's just kind of showing you where the rubber meets the road. Where does the F's and the G's and the D's kind of meet the actual numbers? So a circle's area is a function of its radius. You all know that. A circle's radius is a function of its diameter. In part A, I'm telling you to let F be a function that takes a diameter and turns it into a radius. Write an equation using function notation showing the relationship between diameter and radius. Basically what that means, I want you to write something that looks like y equals f of x, but I want you to use it with the letters that pertain to this problem. So the letters in question here are a diameter and a radius. Whichever one you're starting with goes on the inside. So since it's telling you to take a diameter and turn it into a radius, you're going to say that the radius is equal to f of d, which basically means if you knew the diameter, you could put it into some function f and it would give you the radius. In part B, I want you to now actually tell me numerically what is the relationship between a radius and a diameter. So the radius, if you remember, is always half the diameter. Then look at your answer for part A and look at your answer for part B. They're both R equal. So if they're both R equals, you can set them equal, which means you now have a function that says f of d is equal to 1/2 d. I don't have to break this up into an A and a B. I could just ask you part B, but I'm kind of trying to show you how you would think about it. You have to identify not only the function name f, g, h, but you also need to choose appropriate variables and make sure you understand what is it that you're putting in this case, a diameter, and what is it that you're getting out, in this case, a radius. Similarly, continuation of that problem, look at part C. The g function is a function that maps a radius to a circle's area. You're going to go ahead and write me a general equation, function g, using those variables. So this is the g function, and you're starting with the radius, and you're going to turn that into an area. So area is a function of the radius. In part D, it actually wants you to set up an equation. How are the radius of a circle and the area of a circle related? Well, area is equal to pi r squared. Again, if a equals and a equals, you can now put those together to find one g function, which says that g of r equals pi r squared. Try to make sure you understand what that is saying. That is saying if you put a radius into the g function, you're going to get out the area. Finally, we're going to put those two things together. You're now going to find g of f of 6. So this is composition. You're going to work from the inside out. So f of 6 means we need to go back to our previous slide, and you need to plug the 6 into the f function. So going back here, I'm going to plug a 6 in for the diameter of the f function. So half of 6 is, of course, 3. I'm going to replace that f of 6 with 3, and this becomes g of 3. Then g of 3, I'm going to plug that in here. So that is pi times 3 squared equals 9 pi. So 9 pi is my final answer, but I want you to tell me what that actually means. To tell me what it actually means, tell me what you started with and tell me what you ended with. So here's what this means. A circle with diameter 6 has an area of 9 pi. Basically, the whole point of a composition is you want to skip the middle step. You want to be able to start with whatever the first function is and end up with wherever the last function leaves you. So what it actually means in context is that a circle with a diameter of 6 has an area of 9 pi. This idea of writing these functions and explaining these functions is going to be an important one, but it's also going to be one you're going to get a lot of practice with. So here's homework 9. This is section 1.8 in the book. If you could please go ahead and do these problems. I know it seems like a lot, but it's not quite as long as it seems because some of them are just, add, subtract, multiply, so it shouldn't be too bad. As always, please do that work on a separate sheet of paper, and then you will eventually upload all of your homework at the same time into the class notebook on the day of the next assessment. So thanks very much, guys, and we will catch you next time.